Welcome everyone. In this video we are going to derive the Euler-Lagrange equation, which is crucial for classical mechanics and it is also used for optimization. Let me first describe the setup of the problem. So let's say that we have an integral, and I will be using the physics notation here because I am a physicist at the end of the day. So we will have an integral which I've called S, and it stands for the action. This is the action integral or the action functional, if you were to use some maths terms. And now we will have a time integral. It's, let's say, from time t1 to time t2. And then we have the Lagrangian of the system. That could depend on some generalized coordinates, some generalized velocities, and time. So let's say we have the first generalized coordinate, the generalized velocity associated with that, and then you would have the other ones. Let's say we have n of those. Maybe I should put ... here. Let me just do that better. Right, and then we of course have time at the end. Then dt. As I was saying, this is called the action functional because functions take functions take numbers as inputs and output other numbers. The function, when we're talking about a functional, that will be taking in as output a function. And in our case, I think this is the notation they have. It will take, Q1 through Qn. Because remember, Q1 and Qn, they're all functions of time. We're talking about positions and velocities. So the functional will be taking in functions, and in this case, it will be outputting a number because we've defined the t2 and t1. This is a definite integral, but if you don't include the upper and lower bounds, then you could get a function. But for our case, we're inputting a function and outputting a number. But anyways, I don't want to make it more complicated than it needs to be. S, the action functional. So now we're going to be looking for the stationary, we'll be looking for Q1 through Qn. We'll be looking for the trajectory that makes this action functional stationary, which is the principle of stationary action, which is also called the least action, but that is not true. It is more formally the principle of stationary action. It might happen to be the one that minimizes it, but as you will see in the derivation, we're not talking about maxes and minimums. We're talking about stationary points, stationary functions, stationary trajectories, whatever. So I want to first draw the picture for Q1, and it easily generalizes for any of the other coordinates. Let's say this is the time axis, this is the Q1 axis. And here we have t1 and t2. These are the endpoints, let's say. And let's say the function that makes the action functional stationary is this Q1. This trajectory makes it stationary. Okay? I want to disturb this trajectory a little, and then I will do some calculations which will let us find a condition that Q1 satisfies. Okay? What we're looking for is some sort of condition that these Q1 to Qn satisfy, and specifically these two Q1s, Q2s and Qn's, they are the trajectories that make the action functional stationary. Okay? And I want to, as I said, disturb this path a little. Let's say I keep the endpoints the same, and this is the new trajectory, which I will call Q1 hat. Now, how is this Q1 hat defined? It's going to be the old Q1 plus, you could add any function to it. Let's say n1, which is a function of time, as I was saying, even though I don't write it explicitly. Well, maybe I should at this point, just for this step, I will write it. You could do this, but you can always factor out a number, which I will call S1. I can factor out an S1 from N1. And the reason I do this is because I can, if I were to ask you to take the derivative of Q1 hat with respect to, let's say, S1, let's say, partial derivative, you would say N1. This is really easy for us to do. S1 is a regular variable we're used to, but, you can't really, taking the derivative of a function with respect to another function, that would be a bit weird, let's say, what would this be, let's say? Is it even defined? It gets problematic, so that's why we sort of have the S1 there. And another really important thing here is that N1 vanishes at the boundaries. It is equal to 0 at the boundaries. The reason for this is I don't want to be considering any function, right? I'm not going to look at this trajectory or that trajectory. I let any disturbance to the path that makes the action stationary, but I keep the end points the same. It's as if I have a string that I've nailed at the two ends, and I can stretch the string however I want. So this is the setup, and you can see then, at the endpoints, Q1 hat and Q1 are the same. And when S1 is 0, they're also the same. Anyways. So now what I want to do, and this is the new path for Q1. Of course, for Q2, Q3, and Qn, you would do the exact same thing. You would have, instead of S1, you would have S3 and N3, right? So 1 here is just a placeholder, let's say. Now, if I ask the question, what is the partial derivative? Well, first of all, just before that. So we have the S here, the action, making up new terminology. And now we've disturbed them to new coordinates, so let's write that. Qn. Cool. And this isn't the old one then, this is S hat, let's say. Now, I want you to notice, once we evaluate this integral, what will S depend on? Since we're doing a time integration, right? All of the time dependence will vanish once we evaluate at the boundaries. So this S hat functional will only depend on S1, S2, and Sn. So I could ask the question, which was again why we in fact introduced the little disturbance S here. I can ask the question, what is this partial derivative? Which we can do as follows. So I will take that inside the integral. It's also already a partial derivative, so we don't need to change anything. If it was a full derivative, then when it goes inside the integral sign, it will become a partial one. But it already is a partial one, so that's something we don't need to worry about. And now if you look at this, we will basically use the chain rule for multivariable functions. And it can get tricky sometimes, but this is not one of the places that it does get tricky. This is a standard one for us, but I'm just telling you guys to be careful when you're doing partial differentiation for multivariable functions, because the chain rule might get tricky sometimes, but for this case it is not that tricky. We will only have, well, let me just write it quickly, and if you know enough calculus, it should make sense. Okay, so this is the thing we have now. The good thing is we can evaluate some of these integrals, some of these derivatives. Obviously, you have no idea how to do this because we don't know the function, we don't know the form of the Lagrangian. So we can't do anything for that. Now this one, if you look here, if you look there, we can see that derivative is going to be n1 plus, well, we keep this one again. Then the other factor is going to be, well, if we take the time derivative of this, that's q1 dot plus, S1 doesn't depend on time, it's a number. I mean, it could be any number though, like you get that, right? We're taking the derivative with respect to it. But it says, well, it says scalar, let's say, it doesn't depend on time. And then n1 hat. So here, if we take this derivative, we see that it's going to be n1 dot dt. Now I want to break this integral up to two pieces. So it will be like, so this is the first one. Now comes the second one, which is this part, right? But in fact, I don't even want to write it. Here, I will be using integration by parts. So I will call u as that, which means n1 hat dt will be dv. So n1 will be v and du will be, let's see, d by dt q1 dot, then dt, right? You can think as if I took the time derivative of both sides and then multiply by dt. I know mathematicians doesn't like that terminology, but as far as this application is concerned, you can reason it like that, or it's just chain rule again. Oops. Right? Now, if we now just apply the integration by parts formula, which I have a video where I derive that, you can access that from the cards right now and also from the descriptions part. But it basically tells us that we first write u times v, which is like so, evaluate at the boundaries. Then you have minus, what was it? V du, I believe. So v and then du, which is, I'm copying it down. Cool. And of course we keep the same bounds. Now, actually, here I realize I wrote v. Well, which is correct, but v is n1. So I better write n1. And the nice thing is, the way we were choosing the paths, as we noted here, n1 is 0 at the boundaries, at the endpoints. So, when we evaluate this at t1 and t2, n1 is 0 at both places. So that goes to 0, which gives us this result, which gives us this integral. I will factor out the n1, which might be apparent why I do that at this point. But just bear with me for another few minutes. dt. All right. Now this was just, we just took the derivative of the action functional with respect to S1. That's fine. What we can require now, though, is, we can say we're actually looking for places where, well, I want to evaluate this for S1 equaling 0. Because when that happens, Q1 hat is Q1, which means we obtain the function that makes the functional stationary. So this equals 0 then, because that's, that's literally the definition of that's the definition of making a function stationary. That, well, I hope I'm not making this part more complicated than it needs to be. Basically, when we evaluate this derivative at S1, Q1 hat becomes Q1. And so we're now considering the function that makes the functional stationary, which means that this derivative should be equal to 0. This is the condition on Q1, basically. And so I can now look at here then. The only thing here that changes, could I just copy paste it? I probably should be able to. Well, anyways, I'll just write it. So the only thing that changes is Q1 hat is now just Q1 because S1 is 0. And of course, Q1 hat dot is just Q1 dot because S1 is 0. And if this integral is identically equal to 0 for any n1, remember, n1 can be any function. If this integral is 0 always, that means that this part is 0. And you could have done the same thought process for Q2, Q3, Qn, any of the generalized coordinates. So you would just obtain the general result that dl by dqi is equal to d by dt del dl dqi dot, which is the Euler-Lagrange equation. And here I, goes up to n. Cool. Now, this was all maths up to this point, actually. Even though I used the notation that physicists use, this is all maths. The only physics part that I want to state is that L is kinetic energy minus potential energy. If you choose this Lagrangian and apply it to physical systems, you will see that you get a formulation that is equivalent to Newton's formulation. And you can take this a step even further. Well, I guess further isn't the right word because, they're all equivalent systems. So you could, basically this is equivalent to Newton's formulation, and you can also see that this is also equivalent to Hamilton's formulation, the Hamiltonian mechanics. But this is the Lagrangian mechanics. This is the main formula for it. And as I was saying, this is a maths thing though. You don't need to apply this to physics problems. You could use this to find use this to find that the shortest distance between two points is a straight line. You would consider the distance functional, and then you would see that the slope of the path between the 2 points needs to be constant, which means that it's a function, which means that it's a line. So, as I'm saying, the Euler-Lagrange equation, it's a maths result. The only physical insight here is that the Lagrangian is kinetic energy minus the potential energy. Alright? I hope this video was helpful. If you have any questions, please add them in the comment section. I hope to see you in another video. Until then, take care.